Today's lecture, we can so we're pretty much done with um, the layering stacks with the first three lecture materials on the first three lecture materials. Now I want to move on to switching and packet switching as well as delays from circuit switching, packet switching, and delays, which is also a key part of our information is it's transmitted. I think generally information transmission uh, revolves around switching a lot because we need to know uh, since messages go through various circuitries and various systems, we want to understand how some of these circuitries handle the flipping of messages within itself in terms of um, how to stack up the message and what in the order, as well as how to know where which route to switch it to, or which path to switch it to. Okay, and that's where switching and packet switching comes into play, or that's where switching in general comes into play. And there are two main um, technologies that comes into play when it comes to switching. And the first one is circuit switching, and the second one is packet switching. Packet switching usually handled and the for more or less uh, packet related information, and this is more related for analog information. So these are more for the uh, uh, messages with erratic or non-sequential feeds or bit sequence, whereas packet switching will be more for the messages that have got fixed packets deliveries or fixed packets deliveries, or what's called more or less fixed variable uh, message deliveries. So we'll look at information that relates to these two. We'll get to that part very soon. Okay, so at least we understand um, what some of those uh, terms really mean in terms of how we hand off the messages within systems. Okay, and like I said, that's what this particular lecture is all about. How do we switch the messages, and what are some of the delay consequences that goes with that? Because obviously, if you're trying to find means, um, let me put it this way. Take for instance, I'm going to use an illustration just to help clarify what switching in general is and how delays plays a role. Take for instance, you're on a road, you're on a service road, and you're about to get onto a highway. And to get onto that highway, you have to use an exit ramp. And it's not just you trying to get onto the to highway or the freeway. There are other cars, okay, right? So that whole stack of cars trying to find their way onto the highway uh, would initiate a process, uh, a traffic process that would help determine which order cars get onto the main highway. If say the exit ramp onto um, the highway or even off the highway is it's a multiple lane, then it's the arrangement of the order of how the cars come that will determine how they're going to be switched onto the highway. We all just can't jump onto the highway instantly. If that happens, it will cause a huge accident. So switching in a way within networking kind of look at that aspect of it. How do we manage all that information coming through? How do we switch them so we make sure don't create congestion or there are no delays. We hand them over to a particular path or route that comes. How do we make sure this machine is switched properly to various respective lanes and what have you for the message to just keep flowing on route to the assigned destination? That's what the whole of switching is really all about. Okay? So when it comes to communication networks, there are two main forms of switching. There are two forms of communication networks. Sorry, when it comes to communication network, there are two main forms of communication networks. One is the switch networks, which handles uh, or which address or handles both the circuit switching and then the packet switching. Okay, so the first communication network, which falls within, which is switch networks, it's what handles the circuits and packet switching. And generally, it's said to have the more or less the end nodes sent to one or more end nodes concept under the switched network. So end nodes sending to one or more end nodes is what really falls within the straight network. Now, the other network under the communication network is broadcast network, where it's more or less related to end nodes sharing a common channels, like for instance, TV, radios, and what have you would fall underneath that part. Okay, so here we go. So yes, the two communication networks, switch networks and broadcast networks. End nodes send to one or more end nodes. So, so when you look at whenever you think about switch network, you're looking about how you're looking at for uh, an end node or a device trying to send message to uh, one or multiple devices, or in a way, or or in other words, either requesting or sending. It can either be requesting messages from multiple sources. Okay, so to keep that in mind. Within that part of the switch network. Okay, looking at how multiple nodes can be accessed by one by a given node, by one node or whatever. Okay, or what have you. So that's where you do have the network, the switch networks, so the circuit switching and the packet switching. Circuit switching in generality handles dedicated circuits per calls. So this is where most of your analog transmission happens, whereas packet switching handles most of your data in discrete portions, which is related to the internet. Okay, we'll get into that very soon. But as I mentioned, broadcast network, which falls within the second part of the communication network, handles more of the one end nodes sharing multiple channels. So it's like a TV station broadcasting the information, or a radio station broadcasting the messages to a number of TV devices or radio devices. Okay. So now let's look at, since we're focusing more on these two, remember it was circuit switching and packet switching. Let's try to delve into some of these two and look at what exactly is going on within circuit switching and packet switching. So anyway, when it comes to circuit switching, dedicated communication path or sequence of links of circuits is required to be established between two end nodes through the nodes of networks that are attached to it. So like for instance, you want to make a call on a traditional telephone line. Uh, the the very moment you pick the handsets and you dial the number, the exchange circuits where the dial tone goes to have to try to establish kind of like a physical connection. It's a physical wiring connection between you and the destination phone you're trying to call. That's what we say. It requires a dedicated communication path. And usually when that happens, that circuit that's been dedicated for that particular call, that's when it's whenever the connection when the connection goes through, um, that transmission is always uninterrupted. It's reserved for that particular transmission. It cannot be used for any transmission again, or nobody else, no other device else can use that particular circuit uh, for any other communication. Okay, so once you establish that dedicated circuit for a given call, it kind of remains um, uh, throughout the duration of the call. It's after the call ends that that circuit can be made available again for another device or another phone to use for its transmission. That's where we say it requires a dedicated communication path or a dedicated communication link needs to be established between the two nodes that are trying to participate in a message transmission. And this is where bandwidth, which is defined as a circuit occupying a fixed capacity of a dedicated link for an entire lifetime of connectivity, of connection, or in terms of the duration of that particular call. Capacity is unused by the circuit and cannot be used by any other circuit. So capacity that's in use uh, um, the capacity in use cannot be used by any other circuit in a sense. Okay, so going through. Okay, so a dedicated communication path, which I emphasized on earlier, is established between two end nodes through the node to the networks, and bandwidth, which is the circuit occupying a fixed capacity within a given link for an entire lifetime of the connection. An entire lifetime here relates to the duration of that particular call or interaction between the two end nodes. And capacities unused by the circuit cannot be used by other circuits. So whenever it's engaged, when a specific capacity is being dedicated for a given transmission, the unused part cannot be used by any other circuits unless the circuit or the call ends or the circuit is terminated. So once we allocate a specific amount of capacity for a given dedicated communication path or link, that fixed capacity is what is allocated, and unused part of it cannot be used. There's no contention over there. Nobody can access that. Okay, and that's why they say sometimes bandwidth is a bit underutilized within circuit switching, because sometimes assuming that the you allocate 5 meg for a transmission and only 1 meg or 2 meg is being used, then you have 4 to 3 meg available that's unused. That can't be even accessed by anybody until the transmission ends. Okay, yeah. So in a situation where you have a voice call, and if you've dedicated 5 meg for that particular voice call, and the call took up a capacity of say 2 meg, then you only have 2. Then you have 3 meg that's been underutilized, but unfortunately cannot be used by any other circuit for any other calls. It's until that particular call terminates before the circuit and the capacity can be allocated to another device. So in this sense, latency is where you define how not data is not delayed at switches. So latency is a huge. I'll probably say latency, depending on the capacity of the bandwidth, depending on the bandwidth capacity, latency is not much of an issue. But if bandwidth capacity is quite limited, then latency can be a huge problem. Okay, but generally, once a call is negotiated, there's a reasonable fixed capacity allocated for it that's supposed to address that particular call transmission. So delays are not a huge problem. That's why we say data is not delayed at switch. They just hand it off because it's already been established as a fixed capacity switch or dedicated path. Like it's prioritized link for a given transmission. So it just belongs to that particular transmission for the duration until the termination of that particular transmission. If not, uh, the capacity of that particular transmission is untapped, it's unused by any other circuit. So you do have that uh, room, without much of any issues with delays. Okay, at the switches that would handle transmission uh, for the two end nodes or end devices. Continuing with circuit switching, there are three phases involved in communication processes, especially when it comes to voice calls. First of all, we need to establish the circuit, which is where a dedicated path are initiated, and then we transmit the data. So once we have the dedicated path in place, then we actually transmit the message or the data itself. And finally, once it's all said and done, then we terminate the circuit. So you first establish and you last terminate, and in between you just forward your message. If circuit is not available, busy signals and congestions are what are gotten from that particular medium of transmission. So for instance, this is a scenario where you have two telephone systems, obviously using circuit switching, and a call was made. So once the call was made, once you dial the number, uh, the medium goes to the ent'd circuit and then try to find available circuits that it needs to establish within a given network. Okay, and then that circuit also passes on to different circuits. So in this case, the call came in on this circuit. This circuit decided to hand it off to, or this circuit decided to initiate the dedicated path by allocating the first link to this circuit, and then en route to another exchange circuitry, which also hands it out to a different other circuitry en route to the final destination circuitry. So once that's established, so you do have this link, that link on one exchange point or one exchange circuit to another exchange circuit. So these are the switches, more or less the switches that are handling the dedicated links, and this has to be established first before the message is transmitted. So here we're talking about how the circuit is established. Like I said, once you make the call, when the call is ringing, then the circuits are being initiated. The establishment of the circuits are being initiated. And then once the circuits have been established between the two handsets that want to exchange information, then they basically start transmitting the message. And as we mentioned, the capacity allocated for this particular circuit is only reserved for this particular transmission. Spare capacities cannot be used by other uh, systems or other devices until the termination of the circuit is reached. Before this circuit can be allocated to a different machine for their transmission needs. Okay, so this dedicated path is quite essential, and that's what makes delivery of messages quite reliable with no delays at the switching levels. Okay, so here in the time diagram for circuit switching, we can have it. We notice the way information is being carried from one host to another, and we do have two nodes which are switches handling the transmission flow. So first of all, a circuit is established between the two devices, and there's that agreement between the two devices to transmit a given data. And once the transmission is agreed, then they start transmitting data itself. Okay. And then once the information is transmitted for the given time period, and then it's finally terminated for that circuit, for the allocated circuit and capacity to be reassigned to a different system altogether. So when it comes to within circuit switching, you can see network resources such as bandwidth are usually divided into pieces. Okay, and those pieces are allocated to calls, resources, pieces idle if not used by calling by owning calls. So in that sense, they are not shared, as we mentioned earlier. Once the circuit is established, they can be shared by with any other device. Um, so there you go. Yeah, resource piece idles if not used by other owning calls. So obviously, no sharing is involved. And as I mentioned, network resources and are divided into pieces, and the pieces are allocated to calls. We also do have dividing of links bandwidth into pieces, and these pieces revolve around frequency divisions and time division. So when it comes to circuit switching, which revolves around more of your analog transmissions, uh, frequency and time divisions are key elements within within which bandwidth splits into its pieces. Okay, so we'll get to our frequency and time plays a key role within circuit switching. So we can also find out more about uh, what are some of the frequencies available and how time slots are implemented. So this usually falls within the multiplexing rules. That circuit switching employs a lot. So we'll look at some of those, like the frequency division multiplexings and the time division multiplexings, to handle the switching of the message, or to handle the division of messages, of bandwidth into pieces, to handle allocated services that it needs. Okay, so this is so as I was pointing out, so we looked at um, the frequency division, for instance, bandwidth, and then the time division. So um, frequency division multiplexing is more about it relates more or less about the spectrum allocation that we have um, to help us switch messages from one source to another within a given medium. And here in this example, we're looking at how we splice up a given frequency spectrum that's been allocated for a given circuit transmission. So here we do have 4 users that's been allocated this particular frequencies, and depending on the size of the frequency allocated, we can splice into 4 users. So we have the orange, so we have the blue, is that green, orange, and then purple. So we have 4 users sharing one allocated frequencies, or one allocated frequency. Okay, and we graph this in respect to time. Okay, so we have one frequency, and we can have 4 users uh, uh, split, or we can split up this frequency into 4 users for 4 users to access on a regular basis to handle their transmission needs. So, and like I said, in a way, once a channel has been allocated a given frequency, you can find a way to break that frequency up into uh, a number of layers and use that to address users' needs. So in this case, it's 4 users that are tapping into one allocated frequency that has been split up. So 4 of them can enjoy the frequency. Okay. Now, on the other hand, when it comes to time division, it's the same frequency that's been allocated, but instead of it's been divided at the frequency point or base of the frequency, we use time instead. So for that same particular frequency allocation, we actually say per given time slot, we can split up the frequency. You can slice it up into given time slots and reallocate them for those 4 users for a given time a given time allocation. So if you look at this carefully, you notice that the 4 users have from, say, if you use time from time one to time 4, they have this slice of the entire frequency to operate within at a specific time slots. And at another time slots, they are aligned again or reallocated at different slides of the frequency again, and so forth and so forth for duration. There's 1, 2, 3, 4, actually for 5 duration. 5 duration time slots have been allocated for these 4 users based on the time instead of the frequency. Okay, and now one of the questions that comes up with these two um, division is that which one actually makes much use of the frequency allocated. Obviously, the time frequency makes better usage of the allocated frequency. And the frequency part of frequency division multiplexing kind of like wastes a given allocated frequency. If you notice, we slice up an entire frequency to 4, and there's no time duration for it. There's no time limit. So for as long as you have this frequency, it's up to you to use it anyhow you want, and nobody else can share with you. And this is one of the issues that probably comes up with a radio station's frequency, because once it's allocated to them, even if the radio station is offline, their frequency channels cannot be used by any other person. It's been allocated for them and for them only. For as long as the for duration of the frequency license, they own that frequency. So whether they decide not to operate on that frequency or not, it's really up to them. Nobody else can, tap into that frequency. That's why we say the frequency time division multiplexing, kind of like in a way, uh, 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 does not utilize the frequency efficiently. It doesn't. It kind of makes it unutilized at some point, especially when the frequency is not being used. Because using the radio station as an example, as a TV station as an example, an example of a TV station being allocated a particular frequency spectrum to operate within, and then their transmission just goes off. Nobody can take out that transmission. It still belongs to them for a time duration that they've subscribed for that license for. Okay, so even if the station is off, the systems are offline. If it's 10 years uh, frequency lines that they sign up for, nobody else can use it. If they are offline, they are offline, and that frequency will still be available for them for the entire 10 years duration. Okay, so in that sense, it's kind of like underutilized, right? That's what it means by the frequency division multiplexing.